10.1 Lines and segments that intersect circles. Your essential question, what are the lines and segments that intersect a circle? Okay, before we start, let me start with what is a circle. So I'm just open in your textbook. This is page 530, 10.1. And a circle is the set of all points in a plane that are equidistant from a given point called the center. So if I center P here, then the circle is all the points that are equidistant from that center P. And a circle with center P is called circle P and can be written as, and you just draw like a little circle next to the P. Okay, so that's what a circle is, and that's what we're going to start studying. And we're going to talk about the lines and segments now that intersect the circles. Let's call this circle P. And let's remember that the ways that we can name circle P. So you got two ways, right? First way is you can say circle P. Or a lot of times what you'll see is an actual circle drawn and then the center. So circle P. All right, the drawing at the right shows 5 lines or segments that intersect a circle. Use the relationship shown to write a definition for each type of line or segment. And then definitions are located on page 530 in your textbook, which I already have open, and you might want to open your textbook as well. So let's look at each of these lines or segments. So we'll start with the first one here, which is radius. If I look at the radius, what can you tell me about the radius? Like, what's a way to describe this? Well, the radius starts at the center of the circle. Okay, so one of its endpoints, it's a segment, right? One of its endpoints is on the center of the circle, and it ends on the circle. So another one of its endpoints is on the circle. All right, so let's check that here. So a radius, a segment whose endpoints are the center, and any point on a circle is a radius. Okay, so that's exactly what we just said, and that's exactly what we're going to write down. So it's a segment with one endpoint at the center and the other endpoint on the circle. That's a radius. You've probably been exposed to a radius before. We use radii to find like the area of a circle, which you've probably done in previous math classes. All right, so now let's look at chord. So a chord does not go through the center, right? It doesn't touch the center, but it's still a segment, and it's a segment with just both endpoints are right on the circle. It just doesn't happen to have one endpoint in the center. So it's a bit different than a radius in the fact that it doesn't touch the center, but it is a segment. So in that regard, they're the same, right? They're both segments. But this segment has its endpoints just anywhere on the circle, not necessarily one on the center. Okay, double checking that in our textbook. A chord is a segment whose endpoints are on the circle. Perfect. So we'll just write a segment with endpoints on the circle. Okay, now let's look at diameter. So here's our diameter. Now notice that diameter is also a segment. So in that regard, it's similar to a radius or to a chord. But the diameter does, in fact, go through the center. Its endpoint's not on the center, though. The diameter has both of its endpoints on the actual circle. but it goes through the center. Okay, so let's see what they say for diameter. So a diameter is a chord, okay, that contains the center of the circle. So they're actually using the previous definition, chord, because it's a segment whose endpoints are on the circle, to describe a diameter as a chord that goes through the center of a circle. So now a diameter is a segment or a chord. I'm going to go ahead and say a chord that contains, what that means is it goes through the center. Now another cool thing about a diameter, if you notice, a diameter, if I just take half of that diameter, what do I have? Right, if I just got rid of this, half that diameter is the same as a radius. So radius, I'm going to go back up to radius, and I'm going to say radius is the same thing as half of a diameter. Or a diameter is the same thing as twice a radius, so 2 times a radius. All right, secant. Well, what's different about a secant? Look at a secant. Secant is not a segment, right? A secant is a line. Now, it just so happens to be a line that basically goes through any 2 points on a circle. Doesn't necessarily have to go through the center. Okay, let's see what the book says. So a secant is a line that intersects a circle in 2 points. Perfect. So this time it's a line that intersects a circle in 2 points. Okay, now let's look at tangent. A tangent is also a line, right, similar to a secant, but notice where it's located, right? It doesn't actually go through the circle. A tangent actually stays on the outside of a circle. It only touches the circle at 1 point. All right, let's see what your textbook says. A tangent is a line in the plane of a circle that intersects the circle in exactly 1 point, and that's called the point of tangency. Perfect. So, tangent, again, is a line that intersects a circle in exactly 1 point, and that 1 point is called the point of tangency. Now, secant and tangent lines are super important. I mean, these are all very important concepts for you to understand. But secant and tangent lines go all the way. You're going to keep using those, and they're going to become super important when you get to calculus. So you want to have a pretty in-depth understanding of secant and tangent. You should already have a pretty good understanding of what a radius and a diameter is. And then realizing a chord is just any segment with 2 endpoints on the circle, but not necessarily going through the circle, or through the center of a circle, sorry. A diameter is a special kind of chord. It's the chord that goes through the center of the circle. All right, let's do example 1 then. Tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle O. Right, so this is circle O because its center is O. All right, so looking at segment PR, well, this segment has both endpoints on the circle, which tells us that it's a chord, but it goes through the center. So it's a special kind of a chord, right? This is the diameter. And if at any point you're confused about why I'm writing this, go back and look at the definitions that we just wrote. All right, line MN. Well, the fact that it's a line really narrows it down here, right? It's only going to be one of the last two. It's either a secant line or a tangent line. Okay, so line MN, well, how many times does it intersect the circle? Line MN is only intersecting the circle one time at point R. So the line that intersects a circle in exactly one point is a tangent. Again, line PQ, so we don't have a lot of options here, okay? But we got line PQ. Now it's intersecting the circle in 2 points. Well, what kind of line intersected the circle in 2 points? A line that intersects a circle in 2 points is called a secant line. Now we got segment QO. Okay, so segment QO, notice its endpoints. Well, one of them is in the center, and the other one is on the outside of the circle, or on the actual circle. Well, segments. It can either be a radius, a chord, or a diameter. A diameter is a chord, so let's see. A chord is a segment with endpoints on the circle. I should say with both endpoints. Okay, add that in there. So, does it have both endpoints on the circle? It doesn't. So is it a radius? One endpoint at the center and the other endpoint on the circle. Yep, that's it. All right, a little review. So multiplying polynomials. If you remember when you've done this previously, you basically take your two binomials, right? Both of these are a binomial because they have 2 terms. And you do double distributing. Well, when you do double distributing, that basically means that you multiply the first terms, right? These are the first terms in each of the binomials. Then you multiply the outer terms, right? The ones on the outside. And then you multiply the inner terms, the ones on the inside. And then you multiply the last terms. Well, the cool thing about this, and I'm going to go ahead and rewrite it over here, is when you do that, your inner and outer terms, so these terms and these terms, when you multiply those, so this will give us 6x, and the outside terms will give us negative x. Notice that those are like terms. You combine those and you get 5x. Okay, so where do we see 5x? We see that as our middle term. So your inners and your outers give you your middle term. Your first terms, if you were to multiply our first terms here, we're going to get 2x squared. This was a positive 5x, so I'll put a plus. And when I do my last 2 terms, I get negative 3. So notice I get exactly the same as what they got here. All right, so let's do this one as a class. And I like to implement this FOIL method. I mean, it really is, you're just double distributing. Okay, but I like to implement it because it shows us where our middle term comes from. All right, so first terms. Well, that's going to give me 8x squared. Oh, you know what? Actually, I'm going to go down a little bit. Give myself some room to kind of do this inner and outer thing. Okay, so I'm going to go down here. First terms give me 8x squared. Okay, now, my inner terms give me negative 6x. And my outer terms give me negative 28x. Those are like terms. So if I had just gone ahead and double distributed, I would have had negative 28x, and then I would have had negative 6x, and I would have combined them. And when you combine those, you get negative 34x. And then my last terms give me positive 21. Okay, moving on. Let's use some properties of tangents. So we got a tangent line to a circle theorem. All right, well, if I have in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So what they're saying here is I've got this radius QP. I've got this line M. It's actually touching the circle. It's intersecting the circle at point P, which tells me that if these two are perpendicular, then line M actually is the tangent line to the circle. Okay, so a line is tangent to a circle if and only if the line is perpendicular to a radius of a circle at its endpoint. So we know that line M is the tangent because it's perpendicular to the radius at the radius's point on the circle. It could also be a diameter, right? Diameter is just twice the radius, so if this was a diameter, that same would be true. Okay, so we know that line M is tangent to circle Q. All right, we've got another one. The external tangent congruence theorem. I don't really care much about the names, but I care what they mean. Tangent segments from a common external point are congruent. So if we have two segments that are tangent, okay, so that gets a little tricky because when we define tangent, we defined it as a line. Well, you can also have tangent segments. Tangent just means that it touches it at a point, right? So segment ST is in fact tangent to circle P because it's touching the circle at point T. It's intersecting that circle at point T. And then segment SR is doing the same thing. It's just intersecting the circle at point R. Okay, so if I know that I have two tangent segments coming from a common external point like point S, then I know that these two are congruent. So segment RS is going to be congruent to segment ST. All right, so tangent segments from a common external point are congruent. Hence, we can conclude that these two segments are congruent, which is exactly what this says right here. All right, now let's do some fun math. So we need to verify a tangent of a circle. So is segment ST tangent to circle P? Well, if segment ST is going to be tangent to circle P, notice what it's intersecting here. It's intersecting or touching the radius. Then we would need to know if this is a right angle. And this is going to be a right angle if the Pythagorean theorem holds true. So we can always test any triangle, right? We've got a triangle here. Let's see if the Pythagorean theorem holds true. So in other words, take a leg, square it, add that to another leg, square that, and make sure that it's equal to the hypotenuse squared. Well, the hypotenuse would be the side that is opposite the right angle. And if ST is actually going to be tangent to circle P, then angle T is going to have to be our right angle. So our hypotenuse would be SP. Okay, so I'm going to say 44 is one of our legs. So we'll square 44. $24 would be the length of another leg. So we'll square that. And our hypotenuse then would be SP, or the length of that would be 51, and we'll square that. Now that should be true in order for us to have a right angle, or in order for ST to actually be a tangent. So let's do the math on this. And I'm just going to use my calculator. So 44 squared gives me 1936. And then 24 squared gives me 576. And 51 squared gives me 2,601. So let's see if these add up to give me that. Okay, so let's see, we got 1936 plus 576, and that gave me 2,512. Now that does not make this a true statement, right? These two are not equal. Therefore, we know that segment ST is not a tangent, since triangle STP is not a right triangle. So we'll say no, segment ST is not a tangent, to circle P, because triangle STP is not a right triangle so we know that the radius is not perpendicular to ST, or to segment ST. So I'll say something like, therefore, radius, which is segment TP, is not perpendicular to segment ST. Therefore, we know that ST is not actually tangent to circle P. I'm not sure what it's doing. It might come through here and touch again, right? Maybe it doesn't even touch. I really don't know. Okay, that's example 3. Moving on. Example 4, finding the radius of a circle. So in the diagram, point P is a point of tangency. Okay, so we know for a fact that point P is a point of tangency. Therefore, we know that this angle right here, right, because this definitely is the radius. It starts at the center, goes to P. Okay, this angle right here has to be a right angle. So we're going to find the radius of circle O. And once again, what we have here is we have a right triangle. Okay, so we can basically use the Pythagorean Theorem to figure out what R is. Now, the trick on this one is, what is the length from O to Q? That's the trick. So what do you guys think? The length from O to Q is R, whatever that is, plus 24. So R plus 24. Okay, so I'm going to do leg squared plus leg squared equals hypotenuse squared. Hypotenuse has to be opposite that right angle. So we'll do R squared plus 36 squared has to equal R plus 24 squared. All right, so R squared plus, now what's 36 squared? Just using my calculator here. 1,296. Now this might be a little bit tricky for you. This really is R plus 24 times R plus 24. This is not R squared plus 24 squared. Remember, the inners and the outers are going to give you a middle term. Okay, I'm going to watch you guys mess this up for quite some time, probably a couple years before you get that. That's okay, as long as you get it eventually. All right, so we're going to do R squared plus 1,296 equals, and now I'm going to go ahead and do my double distributing. So R squared, that's my first. My outers, 24R. Look at that. And my inners are also 24R. Eventually, I want you to recognize a pattern anytime you're squaring a binomial. Basically means that the inners and the outers are exactly the same. 24 times 24, just make sure that I got that. 576. Okay, I'm going to combine like terms now. So let's see, I got R squared plus 1296 equals R squared plus, that's going to give me 48R plus 576. Let's get everything, let's get all my R squareds on one side, and let's go from there. So I'm going to subtract R squared from both sides. Okay, so R squareds go away. That's nice. You really like that. So now I'm left with 1,296 equals 48R plus 576. Now from that, I'm going to get my r by itself, so I'll subtract 576. I think that's 720. Okay, and now I'm going to divide both sides by 48. So r is equal to 15. So my radius, right, that's all I had to find the radius of r, or sorry, find the radius r of circle O. The radius is going to be 15. I don't know what the units are, so I'm just going to go ahead and do that. All right, example 5, using properties of tangents. All right, so we've got segment JH is tangent to circle L. Let's see, JH is tangent, which means I know that it intersects right here. And segment JK is also tangent to circle L at K, so right here. Find the value of X. Well, it looks like I have two tangent segments that are basically, they have a common external point, right? They meet at the same point outside of the circle. Well, what was that? Right? Tangent segments from a common external point are congruent. So I know that the two segments then are equal in length, or are congruent. So I can set up a quick equation where I just set these two equal to each other because I know that they're congruent. So I got 61 equals 7x minus 23. They want me to find the value of x, so I'll add 23 to both sides. And then divide both sides by 7. 12. Let's see what I get. Yep. That's it. I don't have to do anything else with that. So this will be some extra practice for you guys to do. So you can do it now, or I'm going to assign it to you when I see you.